This video is about EE533 final project version 2. This week we implemented the project which explores the replacement of a Bloom filter based loop matching accelerator in Snort with a lightweight artificial neural network. This project builds upon the architecture presented in this paper, accelerating Snort NIDS using NetFPGA-based Bloom filter. In this paper, the authors proposed using a Bloom filter implemented on NetFPGA to offload and accelerate loop matching within the Snort network intrusion detection system. The Bloom filter stores hashed values corresponding to a set of Snort loops and performs fast parallel membership checking in hardware. In this Bloom filter based pipeline, the feature input consists of the classic 5 tuple of network flows, protocol source IP, destination IP, source port, destination port. Each feature is hashed using multiple functions, and the hash outputs are checked against the Bloom filter. So what we done is to build ANN and replace the Bloom filter function. I retain the same overall pipeline structure, but with several critical changes. The 5 tuple is pre-processed into a feature vector. And instead of hashing and matching bit vectors, the pre-processed feature vector is fed directly into a chain neural network, and the ANN output is a binary classification, which replaces normal or malicious. Cause the input is only 5 tuple. We can define some alert rules which justify the packet is normal or malicious. For example, we can set this IP as non-malicious IP, or we can use this IP as blacklisted DDoS IP. Here are 32 rules which run the 5 tuple data. And then we should construct and label the dataset. We choose TCP dump to capture real network traffic. Cause we only need the 5 tuple, so I use TSHAG to extract the 5 tuple information. And it stores as the traffic pcap. And then I wrote a Python script to label the data packet. I store the malicious IPs, ports, as well as protocols into the array, and then we can classify every law of the data set is normal or malicious, and then output as the labeled dataset CSV. It is the output is just like here. Protocol, source IP, destination IP, source port, and destination port, as well as label. And just called the ANN inputs is only accept the data, which is number. So we should pre-process the data first. The protocol was one hot encoded. For example, TCP is as 100, UDP is 010, and ICMP is 001. And to be more precise, I separate the IP to 4 segments. First, and every segment was divided by 255 to be normalized. Cause before I tried use all IP as the input, but the result of accuracy is really low. So I separate it at 4 parts, which is the same as the port. The port was divided by O1s. And then I just like the lab 10. I use 1 hidden layer and 3 neurons, but to output. We can to simplify the deployment and for dependency issues, I used Google Colab for training. Here is the data site. It's really like the lab 10 code, except the waits to txt file. And you can see the test accuracy is 92%. And here's the waits file. And then is to simulate the hardware calculation process. the main function is it's a risk calculation. So first read hidden layer weights and then read output layer weights and use for loop to calculate the result. We can simulate. We can debug around this code. We should enter 13 input features. Cause the protocol is one hard coded, so there are 3 TCP, UDP, as well as the ICMP, and the IP is separated as 4 segments. From here, I have translated one law of the data into this input. We just copy it and input here. We can see the predicted is normal, and here is normal as well. And then we should translate the main function from the forward path into Verilog code. I define AN module, and the input is the in data as well as hide and output weights. Output is the out data as well as the predicted class, normal or malicious. All these functions here is really like the CP code of this for loop. But we should we should store the weights, these 2 weights file data into the RAM before. All these work to implement it with NetFPGA is next week. That's all. Thank you.